Good morning, everyone. Is everyone doing okay? You all saw my study sheet, right, for the okay? You know how to prepare for the exam, and it's going to be concepts. When you write a concept, don't write a one-liner, okay? For example, if I ask you what's the induced drag, if you just say it's caused by downwash, you'll get 1 out of 5 points. Every time I explain a concept, I write a lot of pictures to show you step by step what happens. That's what you should do, okay? Like starting vortex, you cannot say it's a vortex shed from the tailing edge of an aerofoil at the start without explaining the physics behind it. So concepts are 5 point probably each, several concepts. Think of it as a 5 out of 100. I need to spend at least 1 out of 20. So if you have a 90-minute exam, you should spend about 4.5 minutes explaining that concept, not one-liner, okay? Also, do not use any AI tools, because I have the same AI tools you have, so I would kind of know what you're doing, okay? So it's very important you grasp the concepts. There'll be some numerical problems, some analytical problems, okay? So that's what we'll be working towards. Most likely today is the exam is just 10 days away. So either this Wednesday's class or next Monday's class will be where I draw a line and say, this is the material we should do, okay? So that's what we are working towards. So last week, we had an online class. So we talked about Prandtl's lifting line theory. This was done by both Prandtl in Germany and also Lanchester in England. So, because of the First World War was going on, 14 to 18, language difficulties, all kind of reasons, each person didn't know what the other one was doing. This was often the case, at the time. But the explanation Prandtl gave was that if you have a wing that is flying in an aircraft flying either towards you or away from you, it doesn't matter. On the bottom side, you're going to have a slightly higher pressure than on the top surface, okay? So if you think of it as a gauge pressure, bottom side will have a higher gauge pressure than the top surface. Remember when you did the X-foil plots, the top surface was more negative than the bottom surface. That's what produces the lift, okay? But right at the wingtip, we cannot have any pressure difference. So the air from the high pressure, Prandtl hypothesized, will rush towards the top from bottom to top in a very visible manner. There's lots of pictures that show this happening. So these vortices will produce a downwash. Okay? So if the airplane is coming towards you, let's say this is the x-axis, okay, it's coming towards you, then the x-axis will be going into the plane of the paper because the free stream is going this way. This would be the z-axis. To the pilot's right would be y-axis, okay. X will be going to the plane of the paper. So this is called a downwash. So this is called a W. It's pointing downwards. Okay. So Prandtl said, as a result of it, if I have a free stream velocity like this, it is coming its own way. As it approaches the aircraft, it sees this a downward directed flow pushing the air downwards. Okay. So you have to vectorially add the free stream velocity that's in the x direction. With a downwards, there's a negative value in the z direction. Okay. So we have a downward directed velocity, W. It's a function of y, okay? It's not, unfortunately, a constant anymore. All over the place. Prandtl, Lanchester, they ignored the fuselage at the time. They knew the fuselage is going to interfere with the lift production of the wing. There's going to be a loss of lift. I'm going to empirically address it. I'm just going to keep a wing alone configuration. Also, at the time, they did not have to worry about the sweep effect, so it was just a straight wing, okay? So they said, I'm going to just keep it as a straight wing. As a result of it, the effective lift direction, free velocity direction was in this direction. Okay. So when you vectorially add the downwash velocity and the free stream velocity, the air was coming at an angle. So this angle is called the alpha I. Alpha I is arctan of the vertical component of velocity by the horizontal component of velocity. This is usually tenths of meter per second. This is like hundreds of meter per second. Okay, so if an airplane is flying at 100 meter per second, 300 feet per second, the downwash will be 5 meter per second, 10 meter per second, very, very small. Larger the aspect ratio, the farther apart these vortices go, the less the downwash. Okay, they already knew something to do with the aspect ratio. By the way, the aspect ratio is you take the wing, project it to the xy plane, so this is the x-axis. Y-axis is usually drawn along the quarter chord line. Okay, so this is the quarter chord line. So sweep was also then measured at the quarter chord line at the time. So it was, if you sweep back, it will be 20 degree, 30 degree sweep back. In this case, it was just a straight, straight wing. Now, the alpha I, the wing area is this projected area is the wing area. We call it as S. The span is called B. Okay, wingtip to wingtip is called the span. This is called B. Then the aspect ratio was basically the span squared divided by wing area. So meter squared is a non-dimensional number. Okay. So large commercial aircraft we see today, going in Atlanta to California or to the Europe, they have an aspect ratio 8.5, something like that. Okay. The reason I think they don't have even longer is because there's not enough gates in Atlanta to fit so many aircraft. But now they are talking about bending the wing down, hinged wing. So when you land, when you go to that gate, then when you're getting ready to take off, you open it up. Okay, that's what I'm talking about. But such large wings have a very large aeroelastic deformations, bending, twisting, and so forth. So now they are talking about trussed wing, where you have a structure attaching the wing to the fuselage to keep it from drooping too low or bending upwards too high, and so forth. So all the old things that were happening long time ago, everything that was drag production, people got rid of them, had a nice streamlined Boeing 7X7 shape. Now they are adding them back because of they want to increase the aspect ratio. Gliders have a very, very large aspect ratio, 10 to maybe 15 even. Okay. Air Force had a project, high altitude, long endurance aircraft, that used a solar power, top surface of the wing was completely solar cells. You just fly around, get the energy from the electricity from the solar power, and then push a little propeller forward, just enough power to stay up, observation purposes. Okay, so so all of these things, they push towards a very, very large aspect ratio. Of course, if you are a bomber, when you are flying, you may have something coming to hit you. So you should be able to dodge it out of the way. You may need to roll, side slip, or whatever you have to do. So bombers had a relatively smaller aspect ratio, I would say maybe 5, 6, so that they could move away out of the way. Okay, a heavy person, like me, I cannot move too far away. Okay, on the other hand, a light person can dodge, right? So that's kind of a situation. Fighters have to do even more interesting things. They have to be able to turn on a dime. So there's one maneuver called Herbst maneuver, where an aircraft comes this way, a fighter comes this way, come to a dead stop, pitches up towards the sky. Okay, this is the upper surface of the wing, this is the lower surface of the wing. Pitches up, then rotate this way, pitch down, and then go. Okay, so during that time, it need to be producing lift at very, very high angles of attack. It's flying this way, right? So the air is coming towards the bottom surface, upper surface is completely separated. So all these things fighters have a smaller aspect ratio, but we would find the closer these vortices are, the stronger the downwash. Therefore, you're going to lose lift, and you're going to increase the drag. Okay, that's why if you watch the movie Top Gun, as soon as you get off the ship deck, a tanker comes and refuels you. Okay, then you travel another couple of 100 miles, another tanker will come and refuel you. You have to keep doing it because of the very high drag, very high power consumption. All right. So anyways, this is what happens. So now if you have an airfoil here, section, originally the lift would have been vertically up this way, but now the lift is tilted normal to the new direction rather than the original direction. Okay, so instead of vertically upwards, the lift vector is tilted backwards. Remember, L prime is a left per foot of span, which is 1/2 rho v infinity squared local chord times whatever is the CL at that particular location. Okay. Now this turning angle is how much is the velocity vector has rotated. It's the same angle as this alpha I. So now you get a backward directed force. That's your induced drag force. Okay, so induced drag is L prime times alpha I. Again, alpha I is roughly in radians. So this is in radians. Okay, so whenever we mathematically write something, it's never in degrees. CL equal to 2 pi alpha, alpha is in radians. Okay, so math speak. So Prandtl said because of that, that's why you get an extra lift. Okay, you get an extra lift. Furthermore, the angle of attack, if this is the alpha, now the alpha has been reduced by this amount, so the CL becomes not 2 pi times alpha minus alpha naught, but I also get this extra induced angle. This is called the induced angle of attack. So this downwash reduces the lift because of this effect. Local lift coefficient decreases, also produces the drag. That's what happens. Okay, that's what Prandtl said is happening. Lanchester also was doing the same thing. Okay, all right. Then came the question of how do I mathematically model it. Okay, so in the homework number 2, we just put one single vortex, then applied the boundary condition at the 3/4 chord point. So Prandtl said, can I just put a single line vortex now? Okay, I have a line here. The vortex is going this way, right hand screw rule. This is my y-axis. This is my x-axis. Free stream is coming along the x-axis, okay, to give you a sense of direction. If you project it upwards, free stream direction is x. It's coming from negative x to positive x, is coming towards you. V infinity I. So y-axis is to the pilot's right, and this is perpendicular to the plane of the paper. So when you rotate x towards y, you'll get could get a z, z velocity vector direction. Okay. So now this vortex is going this way. So this is a gamma of y, because in general it's going to change because the chord is changing. We know the lift coefficient may change because the alpha I may be changing, maybe more downwash here near the vortices, less downwash away from the vortices, and so forth. So everything was changing all along the wing. Okay. Then he said these vortices then bend down here and they become a tip vortex. Okay. So this vortex structure that we saw is visible to the naked eye. Why is it visible? Because inside this vortex particles are spinning very, very fast. Kinetic energy is so high, temperature drops. Okay, it's like a enthalpy plus a kinetic energy is a constant. H plus V squared over 2 is a constant. H is dropping, temperature is dropping. So if you have any kind of a condensation in the air, in the core of these vortices, you get droplets, water droplets. So when the sunlight hits it, it reflects it. That's why we see on some days a trail, tip vortex trail. Other days we don't see it at all. Okay, so that's what happens. Same thing happens with the flap edge vortex. Remember we talked about when you deflect the flap, you are changing the lift so strongly, there's going to be a flap edge behaves like a tip. It sheds its own vortex. You'll see the flap edge vortices. Okay, so anyway, this is the tip vortex. This is a tip vortex. And then these kind of went forever, but they didn't know what to do with it. Then before Prandtl even was developing these theories, this was in the early part of 20th century. If you look at my notes, like 1918 is when everything was codified in the form of papers and stuff by Prandtl. Not because he didn't know this before, but the First World War was going on 1914 to 18. So Germany was on one side, Austro-Hungarian, all those people. England, France were on the other side. So it was not a communication. Things were kind of publicized, okay? Because they already knew airplanes are weapons of war. So why develop technology and give it away and so forth, okay? So, but long before this, Helmholtz had come in the 19th century, okay? We have already seen a lot of scientists in the 19th century, like Euler, Bernoulli, Rankine, and then the Helmholtz. Helmholtz was studying vortex instabilities. When you put a line vortex, it suddenly starts dancing and becomes very unstable. So he was studying the instability. So in that context, he developed a bunch of theorems called Helmholtz theorems, which you're going to see later on today or on Wednesday. So he said a vortex cannot stop in space, free space, because remember, a vortex means rotating particles. So they are rotating about some axis. So they have some angular momentum about that axis, right? So how can the angular momentum suddenly disappear? Of course, if you have viscosity, it may dissipate, convert into heat. But in a pure inviscid flow, there's no way that vortex can abruptly end. So Prandtl said, okay, fair thing. So I'm going to put a starting vortex down in here. That's left when you take off. It's got exactly the opposite direction of my bound vortex. Okay, so this becomes the starting vortex. It's spinning this way from out towards the in. Here it is doing from the front of the wing towards the back of the wing. Okay, that's what it's doing. So the picture is now, just like we saw, this is my circulation over the wing. My starting vortex is spinning in the opposite direction. Okay, positive, negative. Are you all able to see my screen okay, from back there? All right, good. Okay. that was first theorem was Helmholtz was vortex cannot end in space. So then the second theorem, one of the other theorems said, you cannot change the angular momentum very abruptly. Okay, think of a linear motion. Newton's force says a body in motion will remain in motion. That's why you see me walking around the hallway in the morning, trying to do my steps. I also do that on the way from our building to here. Unfortunately, there are a couple of McDonald's, Wendy's and so forth on the way. So that's why I never lose any weight, but that's a different story. So he said, how can the angular momentum suddenly increase, suddenly decrease? It cannot be changing, according to Helmholtz. So Prandtl and Lanchester, I'm sure, said, okay, I'm going to shed a series of vortices, line vortices. These are so weak you don't see them in your naked eye, because the change in the temperature is so small, not a lot of condensation takes place, unless you deflect the flap. Okay, if you deflect the flap, you have a jump in the lift. Okay, then you have a strong vortex at the flap edges. By the way, the flap edge makes a lot of noise. That vortex is bouncing around between the flap and the wing, bumping against this and this, and all these sharp edges of the wing near the flap edge itself, other side of the wing, they produce a lot of noise. So during landing, one of the biggest noises that people see is from the landing gear and the flap edge noise. Okay, now we are talking about the giant, jumbo jets landing near the Atlanta Hartsfield Airport. In the 1970s, when I came, jet noise was the biggest problem. Okay, so Delta would give people money to cover their ceiling, with some kind of a soundproof. They call it a hush money. That's where the word hush money comes from, to keep it quieter, so people won't complain about it. But the jet noise has become quieter because of the high bypass ratio. Are you all familiar with bypass? You have a relatively cold air flowing through the fan. Fan is now producing most of the lift, then coming and then kind of surrounding this high velocity jet. So it's moving relatively slowly, so the jet noise is lowered. During landing, you have throttled down your engine. You just have enough emergency power in case you need to take off, you can't land. But your sound from the engine is lower. Now all of a sudden you start hearing all this noise from other sources. You hear from the flap edges, you hear from the landing gear, anything that is stuck produces a wake, produces buffeting, produces noise. It's like a car. If you open your windshield, just a little bit, the edge of your window will make a noise, okay, as the flow goes around it. In my case, if you remove the floor, mat, you'll see the road underneath. Half the noise would be coming from there, okay? So anyway, noise is being produced. But here, these things are generating circulation. So he said each one of them is producing some small amount of gamma. It's going in this direction, okay? So think of again a right-hand screw rule. It's going this way. It's going in this direction. I'm turning my screw this way. So if I have a gamma here, some circulation, if I add circulation to the wing, this will become gamma plus delta gamma, okay? So as I go from left to right and keep adding circulation, so near the middle of the wing, I have the most circulation. Why? Because it's got the largest chord, and the downwash is not so strong. So right in the middle of the wing, you get a lot of circulation. On the other side, I'm going to take it off. So now my vortices are going to go down this way, down this way. So I'm going to slowly remove the circulation. So left and right are perfectly symmetric. Okay? So you start with zero circulation at the wingtip, slowly increase it to the highest value near the middle of the wing, then slowly drop it to the other wingtip. So this is what he came up with, his model. Okay. Are you all able to see this okay? So this was the Prandtl's model. So he said, if I have a D gamma like this, let's say it at some location, why not? Okay, some arbitrary location, gamma, D gamma, at some value y naught, okay? And if I have some point called P, okay, never mind whether it's a positive or negative, let's say the point is at a location y, the distance between the two is y minus y naught, okay, that's a physical distance. Both may be negative, but this is less negative than this number, so you're going to get say minus 2 minus 3 is plus 1, right? So like that. So it's a positive distance. So the delta W that you get at the point y would be d gamma by, in 2D, 2 pi times r, 2 pi r, gamma over 2 pi r. Remember homework number 2, you said gamma times 2 pi times the distance between the quarter chord point and 3 quarter chord point. Now, because this vortex is not infinitely long, it only goes from 0 to infinity. That means it's starting from here, coming towards you, nothing on the other side, okay, in front of the airplane. So it's half as long as a 2D vortex. So mathematically, it produces half the downwash. So instead of a 2 pi r, it produces 4 pi. R is simply the distance between where the point is and where the vortex is. So this is how you find the dW. Therefore, the W of y is integral of d gamma 4 pi times y minus y naught. All these equations are in the book, in the notes, but I'm kind of explaining to you just verbally what's going on, how his thinking was. Okay, it probably did not happen on the one day. He came up with several different models. Being a German, lots of beer, but not much soccer because Prandtl was not much of a sports fan. Sorry, Felix. Okay, all right. So basically, he was a thinker. He was coming up with a mathematical model. He whenever something heavy math came, he gave it to somebody else. In his group they had a lot of good people. Kutta, mathematician, right? And von Karman later on will join him. He's good mathematics. There are other people there. Okay. But Prandtl was all concept, all imagination. So he made all these contributions. Okay. So in his lifting line theory, I think I have downloaded it already. Where is it? Yeah, I didn't download it yet, so let me download it. So on the AE career day, we were kind of walking through all of these things, right? You remember on Wednesday? And all of these things were explained by Prandtl. He said, I'm not going to get 2D lift. I'm going to get slightly less than 2D lift because of this downwash. And I'm not going to get a 2D drag. I'm going to get a slightly higher drag because of this extra induced drag. So these are the explanations he came up with. Then he said, I'm going to have a tip vortices swirling about. By the way, these tip vortices can stay very, very long distances. So if you have a giant aircraft go up in the sky, if you have small aircraft following it, if it gets caught in the tip vortex, good luck, right? Because you get a high upwash on one side, a high downwash on the other side near the vortex. So if you're following it, then you have a problem. So that's one of the reasons in Atlanta airport, you wait a minute or so before the next aircraft takes off is because the tip vortices from the first aircraft are still around, still swirling about, okay? So FAA has got one of the issues is how do I track these vortices? When do I know it's going to decay? There are a lot of criteria, knowledge people are trying to develop, okay? So tip vortex structure. Anyways, Prandtl came up with this image of the tip vortex. Then he said, I'm producing downwash. Then then he said this downwash is going to produce induced drag because it's a rearward tilt. So we are going to work towards this. We are going to show that this 1 over E is related to those series A3, A1 we are going to talk about later. So it's not a fudge constant. It's going to be CL squared times pi times aspect ratio times 1 plus 3 times A3 squared by A1 squared plus 5 times A5 squared by A1 squared. It'll keep on going forever. So in your homework, the third problem, I ask compare the induced drag of an elliptically loaded wing with what you got with one term in your homework. I will talk about it a little bit later. You'll understand it better. For the same CL, if you had only one term, A3 is 0, A5 is 0, you'll get the same induced drag. But that doesn't mean your straight wing, untapered wing is anything like an elliptically loaded wing. Okay? Elliptically loaded wing has got a elliptically varying lift distribution. It's going to produce the lowest possible drag. So we're going to talk about all those things. Everything we're going to talk about came from Prandtl, at least the physical explanation. Lanchester also did that, but we attribute this to Prandtl theory. So we said all of the circulation, I'm going to put it at the quarter chord line, not distribute along the chord line, or not do like a CFD, which is the far left picture. So I'm going to put the lift distribution along the quarter chord line, lifting line to lifting line, wingtip to wingtip. If I integrate it, I'm going to get a lift. I'm going to not belabor this. All of this we have covered it. So Helmholtz objections were answered by putting series of vortices that add circulation to the wing, and then the vortices don't abruptly end. They end up as a starting vortex here, very far away at the takeoff location. So this is where the vortex is and where the point is. Then you can write that we can write a 4 pi instead of a 2 pi because these vortices are half as long, just a hand waving explanation. Then you get this number. Then you can integrate it to get the downwash. Then you can put that into the CL. Okay, all of these things were done. Then CL produces lift, which is 2 pi times alpha minus alpha naught times alpha I. By the way, if you know the lift curve slope A or A naught, A naught, experimentally measured, you use that rather than a 2 pi because it'll have the boundary layer effect built into it. Like your X file, if you say 2 degree, 4 degree, 6 degree, CL, draw a straight line, you'll have a slightly lower slope than 2 pi because of the boundary layer growth. Basically, upper surface boundary layer grows thicker than the lower surface. It reduces the camber, okay? So basically uncambers the aerofoil. So it reduces the lift curve slope, okay? Lift production, okay? So you get a left. So he came up with an equation like this that he had to solve. So Prandtl then came up with a elliptically loaded wing. So there's some mathematics we covered. So the final bottom line is for elliptically loaded wings, gamma of y by gamma max, if you square it, plus y over semispan b over 2, if you square it, it becomes equal to 1. Okay, it looks like an ellipse. Okay, one of them is a major axis, the other one is a minor axis. So b over 2 is like the semi-major axis, gamma max is a semi-minor axis. Then he used a change of variable. He said, I'm going to use my y equal to minus b over 2 times some angle, cosine theta or cosine phi, whatever, it doesn't matter. Let's see what he did. he did a cosine theta. Then this became cosine squared theta. When you brought it to the right side, it became sine squared theta. Then it became gamma of y equal to gamma max times sine of theta. Okay. So it's a first term in a Fourier series. Okay, Fourier series is a series of sine functions and cosine functions. We will talk about the Fourier series from based on the Glauert's work later. Now, for elliptically loaded wings, why do we call it a load? Load is the lift. Lift is proportional to the circulation, rho v gamma. So if you know the gamma distribution, you know the lift distribution. Okay, so that's why we use the word loaded. It's just the lift distribution. For elliptically loaded wing, this W of y over v infinity is a constant. It produces a constant downwash all over the wing, root to tip, wingtip to wingtip. Also, he proved that this equals the wing lift coefficient by pi times aspect ratio, mathematically. Okay. So there's a few pages of algebra here. If you do everything here, then you get a downwash to be W over V infinity equal to CL times pi times aspect ratio. Okay, this is what we get. As a result of it, the CL became 2 pi times alpha minus alpha naught minus alpha I became 2 pi times alpha naught minus constant W over V infinity, which is a constant, which is some constant over pi times aspect ratio. Okay, so this is what we got for the lift. Okay. Now he said, how about the drag? Since I know how much the velocity vector is tilted backwards, if I take this CL and multiply by W y over V infinity, which is alpha I, and integrate it, I can get the drag. Okay. So a lot of the mathematics was done by Prandtl, and finally he said for the elliptically loaded wing, his CDI works out to be CL squared times pi times aspect, divided by pi times aspect ratio. So if you have an elliptically loaded wing, this is what you would get. Okay. In your homework number 3, if you have 2 terms, you'll get a slightly higher induced drag. Okay, you'll get a 2 terms, A1 and A3. Okay. An infinite number of terms are needed to represent a continuous variation. Okay. All right. Furthermore, if you're going down in here, the C lift also becomes similar picture. This is the sectional alpha, sectional angle of zero lift. This is a constant. So when you integrate it, you also get the CL equal to 2 pi times alpha minus alpha naught minus CL over pi times aspect ratio. Okay. Why do I use A naught here? A naught is the experimental value. 2 pi is the theoretical value. So if you have an experimental value, use it, it's better. Otherwise, use a 2 pi. Okay, so I'll also in the exam or in the homework, I'll tell you use 2 pi or some physical number. Okay. So grouping all the CL to one side, we get 1 plus 2 pi is A naught, okay, times pi times aspect ratio times CL equal to A naught times alpha minus alpha naught, okay. So either 2 pi or A naught. A naught is the measured lift curve slope or a CFT based lift curve slope. Nobody believes the CFT here except the one who did the calculations, right? But let's say you have a lift curve slope computed or measured, you put this in here rather than a 2 pi, otherwise use 2 pi. Okay, so sometimes I will use 2 pi, sometimes I will use A naught, just to keep you all guessing. Okay, so now if you do a DCL D alpha, DCL D alpha, you get the A naught, just the A naught. Therefore, for all of these are for elliptically loaded wing. The lift curve slope is less than the 2D lift curve slope, okay? So you get a slightly lower lift curve slope. Smaller the aspect ratio, the bigger the denominator, lower the lift curve slope. That's why again the fighter aircraft will have a lower lift curve slope than a bomber aircraft, than a commercial aircraft, than a glider. Okay, the aspect ratio, bigger the aspect ratio, smaller this A naught over pi A aspect ratio, so you approach the 2D behavior. Okay. So these were all elliptical. Prandtl could do only one term. Then came Glovert. So Glovert said he assumed a Fourier series. Notice the units of gamma is velocity times distance. Remember V dot ds, it's a circulation. Velocity times distance integrated over a contour. So it could have a units of velocity times distance. That's why we put a V infinity outside the sigma, which is a constant. B, which is a span. Again, that's a distance. Velocity times distance is taken out. The number 2 shows up because everywhere he was getting a 1 over 2, so he grouped them all together, brought it outside. Okay. So 2b V infinity is a constant. Inside, he put an infinite number of terms. Okay. This was just the first term in that series. Okay. Prandtl's theory is the first term in that infinitely large number of terms. Glovert did not include cosine terms. Remember, this is the wingtip to wingtip minus b over 2. This is y equal to plus b over 2. We did the definition here, y equal to minus b over 2 cosine theta. Okay. Now, that means here theta is 0, here theta is pi. Okay. Right here, theta would be pi over 2, 90 degrees. So 0 to 90, back to 180. Okay, that's what the distribution is. He did not have any cosine n theta because cosine of n theta at the wingtip and wingtip, cosine of 0 is a finite number, cosine of n pi is a finite number. Okay, either a plus 1 or minus 1. So you're going to get a finite loading at the wingtip. So cosine of n theta would yield non-zero gamma at wingtips. That's not good because at theta equal to 0, you'll get some non-zero contribution. When theta equal to pi, you're going to get a non-zero contribution. So we don't want that. So that's why Glover did not use anything at all, like that at all. Another thing is, he said, I'm going to only use odd terms. because all terms are symmetric. That means the left wing and right side of the wing will do the same thing. For example, if you look at theta equal to 0, theta equal to pi, remember this is the middle of the wing here. If you plot a sine theta, it will be symmetric, right? So the left side wing, right side wing is going to produce the same lift. So the aircraft is not going to roll one way or the other. It's going to be straight and level as expected. Okay. On the other hand, if you put a sine 2 theta, theta equal to 0, theta equal to pi, you'll start with 0, you'll reach a maximum value somewhere here, minimum value somewhere here, you'll get to this type of stuff. One side of the wing will produce more lift than the other side, you're going to get a roll. So if I ask you why did Glavert use odd terms only, you should be able to explain it. So if you're sitting like this, you won't know the answer. Okay? Hopefully you know it. Okay? But it's very important you understand it. Why didn't he take a cosine terms? You need to be able to explain it. Okay? It's important that we grasp these concepts. They did not arbitrarily delete or remove terms. They kept some of the terms for the series. So in Glavert days, this was done by Glavert. He's a British guy. He was much later, I would say 1930s, 1940s time frame. So that's when they were doing it. They already had a mechanical calculator, some kind of a electrical calculator. Have you heard of vacuum tubes? They were predecessors to transistors. So vacuum tube, transistor, then the chip, then an iPhone. That's the end of the mankind as we know it. Okay? After that, nothing was discovered because everybody was scrolling to see what was done in the past. Okay. Anyway, so he used a finite number of terms, but with the mechanical calculators, they could do it 1 term, 2 term, 3 term, 3 by 3 system very, very easily. In our homework problem, you're going to do 2 by 2 system. Okay. All right? So he threw all of this into the downwash. He integrated it. He put it in here. He got a system of equations. So if you know the angle of attack at a few points on the wing, at those points, you can apply this equation, solve for A1, A2, A3, AN, and so forth. So in our homework number 3, you're going to apply it at 2 points. Because all of these are based on integration, 2 points are best to do not at 0 degrees because nothing happens at 0. Sine of n theta, sine of 0 will be 0, nothing will happen. So you apply definitely at the middle of the wing, pi over 2, then at pi over 4. Okay, so we are going to do pi over 4 and pi over 2. That gives you the best accuracy. Just like in homework number 2, putting the boundary condition at the 3/4 chord point, they found gave the best accuracy. So think of it as a trapezoidal rule. If somebody gives you, find a area under a curve, you won't just pick a random point, right? You would pick somewhere halfway between, find the ordinate times the width. It's a crude approximation of the area under the curve. Okay. So people said, I'm going to take middle of each segment. I'm going to divide it into n segments since I have 2 segments. So I'm going to do it at pi over 4 and pi over 2. So that's what we are going to do. So here is a worked out example that we went over. By the way, once you know A1 and A3, A5, etc., you can solve for the CDI. So the first term is a elliptically loaded wing term. Then the rest of them are non-elliptical loading effects, okay, for a general wing. Okay. All right? So then we did a worked out example. Your homework number 3 is similar to this. By the way, if I don't give you in feet or meter, if I just give the symbol rectangular wing B over C, you don't need to know what is B, you don't need to know C. All you have to know is what is that B over C. If we have an aspect ratio 10, span is B squared, wing area is B times C, So B squared over BC is B over C is the aspect ratio for a rectangular wing. Okay? So you should be able to think through it. If I don't give you all the information in feet or meters, don't get alarmed by it. Okay. So we apply it 2 times, then we get the answers, 2 by 2 system. After you get the answers, you take a A1, you get a CL. Then since I only have 2 terms, n squared by A1 squared is just 1. 3A3 squared over A1 squared, I get my CDI. So in your homework, you're going to follow this example for the first problem. Okay. The second problem, you're just taking one equation. So you don't have A3 anymore, you only have A1. If you have only one term, where would you apply it? Would you apply it at 45 degrees or 90 degrees? What do you think is the most logical place to apply this equation? Remember, if you have a curve, if you want to find the area, you find it at the middle, right? Wingtip is theta equal to 0, other wingtip is theta equal to pi. So where would you apply it if you had one term? Any answer? Anybody knows? Yes, sir. 90 degrees, halfway. Okay. So in the second problem, you'll just do it at 90 degrees. But these terms require, see, span over chord. For a rectangular wing, span over chord is just aspect ratio. Okay? So if you know aspect ratio, you know that. If you have a twisted wing, alpha naught is going to change root to tip. If you have an untwisted wing, alpha naught is going to be 0. Okay? If you have a symmetric aerofoil, alpha naught is going to be 0. Cambered aerofoil, alpha naught is going to be non-zero. Twisted wing, alpha is going to vary all over the place. Untwisted wing, alpha is going to be a constant. Okay? So anyways, these are things we can know and we can apply. So after you have done your homework, you may want to check your answer, right? Did I get it right or wrong? So I have a MATLAB code that I'm going to run. Okay? Anytime I run my codes, there's always a danger the class will end quickly because the program bombed. Okay? In this case, we'll meet again on Wednesday. Okay? But let's see what happens. So if you go to our website, by the way, in the exam, if I give you a problem, do it by hand because that's where you get your answer from. Your grade for. But you can certainly use my code, Prandtl lifting line theory. Prandtl.m and then run the program, okay, if you wish. Okay. So let me go to the download here. I have a Prandtl.m somewhere here. So let me open it with MATLAB. Okay. So it's got lots of, a lot of prompts and comments and so forth. The number n you see on line number 19, I'm setting it to 2 right now. That means I'm just going to take 2 terms. Okay. If you set it to 10 or 11, you'll get a much more accurate solution. 11 will produce 11 by 11 system of equation. 2 will produce 2 by 2 system. 1 will produce 1 by 1. Okay. So I'm going to just keep it as 2. So I'm going to try to run our homework, our worked out example in the slides with this program and see what happens. Quoted by Ellen, lowercase Sankar, okay, being, and it was also done in 1998 BC, by the way, before computers, okay? So that's what happened, okay? All right. As I told you, Prandtl was a friend of mine, okay? So, and you, sir, are no Prandtl, okay? All right. Anyway, root card, input the root card. So you go to the PowerPoint slide. The root card is 2.381. Units will cancel because B over C, as long as B and C are the same units, okay? Input the tip card. We are going to put the tip card as 0.953, 0.953. What is the span? The span was, does anybody remember, 15 feet? Then what is the twist angle? What does the problem set say? The wing uses cambered oil, it's untwisted, so there is no twist angle. Tip is not twisted. Otherwise, it'll assume linear twist usually, okay, root to tip. Okay. Now, what is the lift curve slope? 2 times pi. So you can compute it in a calculator, or you can just 2 star pi. May work sometimes. What is the lift curve slope in the tip? It's the same number. Okay. Now, what is the angle of attack in this problem set? I believe it's a 4-degree angle of attack, 4-degree geometric angle of attack. What is the camber zero lift angle alpha naught? It was minus 1.2 degrees. Minus 1.2 degrees. It was a cambered aerofoil in this example. Okay. Now, as soon as you hit a return, it'll print you a bunch of stuff here. So let's see what happened. It produced a straight line, lift distribution. Okay, we only have two terms, so it's taking 2 points and then drawing a line. Okay. Anyways, so if you go up here, you could see that it has produced A naughts. Okay, so let's look at where do we store my coefficients. When I solve it, I'm going to get a A1, A2, A3, etc. Okay, so those are the constants. So let me use the symbol A for the symbol for the array. Then I'm going to get 2 numbers. So the first number is A1, and the second number is A3. Okay, so you could, by the way, run your homework with this, compare your answers with this. Even in an exam, I will allow you to do that. That will be one exception. You can use computers, not AI, because my program is brain dead, so there's no intelligence anywhere in this thing, so you are welcome to use it. Okay? So you can use it. So this is what we get. Then if you look at the CL, that we computed, a lift coefficient, CL, you'll say CL is 0.4717. Let's go to the homework problem here. .4713. Okay, so it's pretty close. Obviously, we are doing on a computer 2x2 system, which you could have done by hand. Okay, but the beauty of the Glover series is now if you have a 10x10 system, so if you go in the MATLAB code and change this number to 10 or 11, okay, let's put 10 terms. Now run it. It'll ask you the same questions all over again, right? Then you have to put the input numbers. Then it'll give you the n numbers, A1, A3, A5, A7, up to A19 or A21, something like that. Then it'll give you a more accurate CL, more accurate CD. It'll produce a smoother lift distribution. Okay? So by Glover's time, mechanical calculation, it is asking me all these questions. So you have to put in all these numbers all over again. In MATLAB, you can just use an upper angle to go, where you need to go. Upper root card. Tip card is, 0.953. Span is, does anybody remember the span? 15. Okay. There's no twist. There's no twist. The zero lift angle is minus 1.2 at the root, minus 1.2 at the tip. Angle of attack is 4 degrees. 2 pi is 6.28317. 6.28317. Now it produced 10 terms, for your A coefficient, A. Now you have 10 numbers. Do you see that? There are 10 numbers. And notice that the numbers are getting smaller and smaller. So it's a convergence series. Okay? So Fourier series have a nice thing. Each term is orthogonal to the other term. Sine theta times sine of 2 theta, if you integrate it, it'll give you 0. They are perpendicular to each other. And also in a Fourier series, there is a convergence. As you keep on adding terms, it's going to go to 0. If you live well and come to my class at 8 o'clock regularly, okay? He's not paying attention to me. Hello? Hi? Okay. All right. Anyway, I didn't mean to pick on anybody. Sorry about that. Okay? This is why I get such bad course instruction online survey. So I'm going to behave myself the last 2 weeks of the class. I may even bring donuts to the class. Okay? So, all right. So this is the program that Prandtl wrote. Not Prandtl. Glovert formulated it, that we can cast it in a program form. Okay? So this was what was done. Okay. Are you all able to see? Okay? Now we have just a few minutes left. I'm going to talk about some devices we see on aircraft that take advantage of tip vortex structures. Okay? So I'm going to talk about some devices on aircraft. So let's say that you have a wing, okay? Your designer has designed it very nicely, and it was working well in the wind tunnel. But when you start flying it, suddenly, let's say you get a separated flow, okay? So all of a sudden you get a separated flow here, somewhere on the wing. So your aerofoil is producing attached flow, suddenly some separated flow, unexpectedly. It's too late to change the wing, right? Because customers are waiting to buy the aircraft. You have already given a manufacturing order. Hundreds of wings are being built, and being assembled. Too late to fire the designer because he has come to Georgia Tech to teach the aerodynamics class, I used to work at Lockheed, okay? So it's just a part of my biography. So what do? You have to get rid of this vortice somehow. That means you have to somehow mix the external air, which has got a higher velocity, with the separated flow, which is the lower velocity, to mix it up. Okay. So what they would do is, on top of the wing, they'll put a tiny wing-like structures. We call it a vortex generators, okay? Vortex generators. They are well outside the boundary layer, by the way. It's not inside the boundary layer, so don't think of it as it's try to change the turbulence inside the boundary layer. It does not do. It's sticking outside the boundary layer. You can see with your naked eye. Whereas the boundary layer is like a 1 millimeter thick, maybe 1 centimeter thick by the time the trailing edge. It's not that big. So what it does is it is producing its own tip vortex structure. So the tip vortex structure is taking the outer air, pushing it into the boundary layer, energizing the boundary layer. Okay? So if you put some vortex generators, stick it on the surface, they will produce vortices. These vortices, they are outside the boundary layer, so they grab the high velocity flow outside the boundary layer, they push it into the boundary layer. Okay, then it gets absorbed inside the boundary layer, energizes the boundary layer, gets rid of the separation. Okay. So this is how during the flight test, if you see some bad separated flow, this is how you will do it. By the way, how do they know it's separating here? They will put a little tufts. Tufts are like a cotton fiber or a nylon fiber. If it's fluttering about over the wing, it means the flow is separated. If it's nicely aligned with the body, it means the flow is attached. Okay, so they can look at the fiber behavior. They will say, look there, the flow is separating. Let's put a vortex there. So the first generation aircraft, when it rolls off the assembly, will have lots of vortex generators sitting all over the place. So this is what they do. Then next generation, they will clean up the wing. They'll get a new designer and maybe improve the design, get rid of the points. Then you have a good, nice flow. Okay? So vortex generator is a concept that we should become familiar with. I have shown it in here. Okay? So I have some pictures of it. So let me show you how it looks like. They look like a little wing on top of the airplane. They're sticking up, okay? And they take the vortices and then they push it in. Let me see if I have a better picture. Okay, so attached flow, separated flow. They have shown it as it's a trailing edge separation, but it could be separating even in the middle of the wing unexpectedly. Then if you put a vortex generator, it energizes the flow by bringing the outside air into the boundary layer, keeping the boundary layer attached. Okay, that's the vortex generator. So you will see them all over the plane. You know, if you go Google search it, so. You will see, hopefully, some pictures. Let me see. You see the vortex generator there? This is the vortex generator here. You see that? So it's just stuck up on the surface.
Vortex generators are little nubbins that sit on top of the wing.
Okay. Anyway, you can read about it. Okay. And the reason I turned it off was they will explain it better than I do. And it'll be even worse, right? From my grading purposes. Okay. By the way, some aircraft, what they would do is, especially the fighter aircraft, they will produce a notch on the leading edge, if you see it. Okay. The card will abruptly discontinuous. So what happens is, this produces its own vortices, its own tip vortex. It flows over the upper surface. So some fighter aircraft, they have to operate at high alpha. Remember I told you? They may need to operate at 20 degrees, 25 degrees, even more. So when you operate at such high angle of attack, the upper surface completely stalls. You cannot perform the maneuver you're supposed to do, or you cannot turn, you cannot roll. But this vortex from here will produce a vortex generator-like effect and keep the flow attached. Okay. So these are sometimes called chines or leading edge extensions. So I have a bunch of devices that are shown in here. Okay. You have to kind of look through it. I'll come back and maybe I will explain it a little bit better. You know, if you click on it here. Not a good picture, sorry. So that they will have it. Sometimes they will also have this is the fuselage, this is the wing. They will even have a bump like this. This is like a cuff, like over my thing. So it's got a little bit of a projection to it. So the purpose is to produce two vortices from the two edges. It flows over the upper surface, keeps the boundary layer attached on the upper surface. So that's what they would do. All of these things are done, especially in a fighter aircraft, to keep the flow attached. Okay. If you look at F-18 type of an aircraft, they will have something called a leading edge extension. This is the wing. This part is the leading edge, kind of instead of going straight, they add a little bit extension to it. So they call it LEX, or a leading edge extension. The purpose of this LEX is to produce some vortices, from that edge to keep the flow attached. Okay. At Lockheed, they have F-15. They had vortices coming off the wing of the F-15. As they flew over the twin tail, the tail started shaking. It started cracking. Okay, so they came to Georgia Tech. Right here, Lockheed, Georgia, is where all the aircraft that are going to be fighting in the Europe are, housed here, or they are responsible for it. So they came to a Professor Hanegood in our school. He came up. They came and talked about what's causing these vibrations. What can we cause it to suppress it? So Professor Hanegood had a structural dynamics. He's a structural dynamics expert. So he had a structural dynamics research going on, actively control the vibration, reduce it. We had a great professor called Professor Kumarat. He was doing a wind tunnel test of F-15 wings and then tried to show this is what's happening. These vortices are become actually unstable. So if you have a vertical tail somewhere here, vertical tail, twin vertical tail, the vertical tail starts shaking, cracking. Okay, so every few hundred hours, they had to replace the tail. Very, very expensive. And I was fortunate to be on the team. I did a CFD-based solutions, and we kind of got a size of the vortex, strength of the vortex, circulation around the vortex. We could quantify it and then guide the control aspect of it for Dr. Hanegood. So it was a big project. Okay? So F-18 faced the same type of a problem. This leading edge extension vortex will sometimes go over the tail, and the tail will start. Their tail was a little bit like this, like a V tail. So anyway, when vortex hit, it started shaking like this. Okay. So there's lots of very interesting experiments that have been done. These are all based on the devices. So on Wednesday, we will review these devices very quickly. Then we will go to the next step, which is the more general wings. Okay? Thank you.